Hello everyone, today we are talking about the last topic in our optics unit for AP Physics 2, which is interference, and starting to talk about the wave nature of light as well. So we already talked about earlier in AP Physics 2, also in AP Physics 1, the principle of linear superposition, which essentially says that if you have two waves that are in the same place at the same time, they interfere with each other, and really you're just adding or subtracting their amplitudes. So this is true for sound or pressure waves. It's also true for light waves. So when two light waves interfere, it is their electric fields that are combining according to this principle of linear superposition. So if we have sound waves that are interfering, we will hear a difference in the loudness of the sound. So beats, for example, if you remember that from AP Physics 1, if you have sound waves that are slightly different frequencies, you can hear that loudness changing with its own frequency. So for light, obviously, if light is interfering, we're not going to hear anything, but we will see differences. So for light, with constructive interference, you'll have a light that is brighter. For destructive interference, you would have an area of darkness, or at least the light would be dimmer. So constructive interference, to recap, is when two waves interfere crest to crest or trough to trough. We would say that those waves are in phase. And if you have two different sources of light, for example, and you want those waves to interfere constructively, the distance between the source and the point of interference, so where you want them to actually constructively interfere, has to differ by an integer number of wavelengths. So your distance has to be a multiple of the wavelength in order to get constructive interference at the location you want. For destructive interference, which is when the waves interfere crest to trough, and we would call that out of phase, that distance between the source to the point where you want the waves to interfere has to be different by an odd integer number of wavelengths. So essentially a multiple of half a wavelength, and you would have a location of darkness there. All right, so just some vocab. A coherent source is something that emits waves that have a constant phase relation. So they're always in phase, for example. That is a laser. You can tell that looking at a laser, the light coming out of a laser, that light looks very different from the light coming out of the light bulbs in your house. So those would be incoherent sources, we would say, but something like a laser would be a coherent source. All right, so the famous double slit experiment, Thomas Young's double slit experiment, showed that light waves do interfere. And from the experiment, he was able to determine the wavelength of light. So this setup is very common for AP Physics 2 problems. So you have your light source, which would be like over here to the left in these pictures. And then you have your slit. So we have slit 1, slit 2. It's the double slit experiment. So there are going to be 2. So you're shining your light through that double slit. And then you have a screen here. And it'll show you your dark fringes and your bright fringes. They're called your areas of brightness and your areas of darkness. So here you have light entering through the slits, and these two distances from the slit to this point are equal to each other. That's what the L1 and L2 is saying. So your waves are going to constructively interfere right here, and you would have a bright fringe there. That would be this like center bright fringe right there. Now you could also have light waves coming in at different angles. So let's say you have this here, and that light is traveling some distance L1 to reach this point on the screen, and then you have light here, and you can see, like we just talked about, the difference in these two paths in this case is equal to one wavelength. So that's constructive interference, and you would have a bright fringe there. Maybe that's this one or this last one over here. And then for a dark fringe, the difference in the lengths of these two paths is equal to half a wavelength. So you would have destructive interference there, and you would have a dark spot like you do on that image to the left. Okay, so a couple of equations. If you want to solve for the bright fringes of a double slit experiment, these images are helpful in seeing like what these variables are referring to. So you can use sine of theta equals m times lambda divided by d. So M is called the order of your fringe. So this diagram is very useful because that center bright fringe we say has an order of M equals 0. And then you can see that the bright fringes are numbered from there. So if you wanted to solve for that, bright center fringe, M would actually be 0. Lambda is obviously your wavelength, and then D is the width of the actual slit. If you wanted to solve for the dark fringes, the only difference is you have to include that 1/2, because remember the difference in our paths has to be equal to half of a wavelength or a multiple of half of a wavelength. So your order is essentially the same, but you have to have that 1/2 in the equation. All right, then there's also something called thin film interference. So let's say a very common example of this is a film of gasoline on the surface of water. So interference can occur when light strikes a thin film perpendicularly. So you have incident light that's coming in. Part of that light is reflected and the other part is refracted, which we've talked about. But that refracted part, which would be this part here, you can see it refracts at a different angle than that incident ray. Part of that can actually be reflected from the bottom layer of that film. And think about a layer of gasoline on water. It's probably pretty thin, but the light can actually reflect off of that bottom surface of the film, travel back through the film, and then refract back out. So that is thin film interference. An equation relating to this says that the wavelength that is important for thin film interference is the wavelength within the film, not the wavelength in a vacuum. So if you wanted to figure out what is the wavelength of my light when it's in the film, you would take the wavelength in a vacuum, where you would be using the speed of light in order to solve for that if you knew the frequency, and divide that by n, which is our index of refraction, which you can see in the images here. For gasoline, it's 1.4. So that would give you the wavelength in the film that is important for this interference to work. So when light travels from a small to a large refractive index, reflection at the boundary occurs along with a phase change equivalent to 1/2 the wavelength in the film. When light travels from a larger to a smaller index of refraction, there is no phase change upon reflection at the boundary. Okay, so diffraction. Diffraction is the bending of waves around obstacles or edges of an opening. So if we're shining light through a slit, it is being diffracted. It's kind of bending around that opening and is able to light up an entire screen that's much wider than the slit itself. We have Huygens' principle, which says that every point on a wavefront acts as a source of tiny wavelets that move forward with the same speed, and the wavefront at a later instant is the surface that is tangent to the wavelength. So you can see that here. Let's say we have a wall containing a doorway, and we have a sound wave coming towards that doorway. That interferes there. You have these little wavelets, but really you have essentially one wavefront that's composed of many wavelets. So if we shined a light through a slit and there was no diffraction, the light would look like this, which would look kind of weird if you were standing there maybe. If we shined a light with diffraction, you would see that this almost looks like a projector screen. You would see that light spread out on the screen. Okay, and then to solve for dark fringes, specifically for single slit diffraction, which I feel like I do have to do pretty often for AP Physics 2, here's our equation. It's very similar to the other equation for the double slit experiment, but notice we don't have that 1/2 term, so it is sine of theta equals m times lambda divided by w, where w is the width of the slit. So they're just using capital W instead of D there to differentiate. And that is it, everyone. So good luck with your optics unit. I hope everything is going well, and let me know if you have any questions.